Hello, today I'm going to introduce our work, CLARION Sound and Clear Provenance Checking for Microservice Deployments. My name is Xutong Chen, a PhD student from Northwestern University, advised by Professor Chen. This is also a joint work with Hassaan Irshad, Dr. Ashish Gehani, and Dr. Vinod Yegneswaran from SRI International. Many thanks to my amazing collaborators. Linux container-based microservices have emerged as an attractive option to traditional virtualization as they enable better resource utilization, leading to increasing practical adoption. Containers serve as the underlying portable and lightweight software isolation technique. They are facing a new security challenges like container escape attack and malicious crypt miners. As a state-of-the-art host forensics monitoring solution, provenance tracking is naturally transferred from traditional OS scenario to container scenario. But is this transfer really straightforward? It's an open question. Here we start with a motivation example of a trivial insider attack. Three major steps in this attack includes touching the password file, setting up a backdoor, and finally connecting the backdoor from remote. Assuming this insider wants to damage both the container host and the targeting container, those three steps are performed both in the host and inside the container. We will only drill down the first step in the next slide for simplicity and motivate our work by illustrating limitations in the provenance graph from three contemporary solutions. As a container-aware but not namespace-aware solution, WinOver fails on Soundness where we can see the fragmentation in bash cat provenance and the ambiguities on password files. It looks like cat 3030 just comes from nowhere because it doesn't have any parent process. Plus, those two cat processes are trying to read the same file, which is definitely incorrect because we know they should read the password file inside and outside container correspondingly. Just being namespace aware is also not enough, as we can see that CANflow fell on clarity in this graph. Although the provenance is complete and correct, they don't get a clear insight about which subgraph corresponds to a container at first glance. When things come together, spade fell on both soundness and clarity, which would be a huge problem in provenance tracking for sure. By being namespace aware and container aware, our CLARION solution provides a sound and clear provenance graph as you can see here. So the contribution of CLARION can be summarized here. CLARION provides the first in-depth analysis of the implications of namespaces on provenance checking. CLARION is the first namespace-aware and container-aware provenance checking solution. We implemented as an extension of the SPADE provenance engine. The detailed implementation involves kernel module, net filter hook, and modification to SPADE application level handlers. Detail can be referred from the paper. CLARION is tested by a comprehensive evaluation of effectiveness, efficiency, and generality. Dive into the soundness challenge we observed in the motivation example. We found that the root cause of it is the inconsistency in the low-level events. This inconsistency occurs when low-level events report data from different contexts and results in vertex splitting in the provenance graphs. Consider the clones Linux audit event as an example here. Its PID field 5903 is in host context, but its exit field 2, which is also a PID, is affected by PID namespace and is in container context. If provenance tracking system directly uses those two data fields to generate provenance, data fragmentation will definitely occur. Starting from PID namespace example in the previous slide, we did further in-depth analysis on namespace implication about how and what in provenance tracking can be affected. According to the result table, we can see that PID, mount, network, and IPC namespaces impact soundness very much. Additional details can be referred from Table 1 and 2 in the paper. As one last step to show the severity of soundness challenges, we give some results on investigation about soundness challenge on other Linux audit subsystems and OS platforms. As you can see, soundness challenge persists under most cases in other Linux auditing subsystems and OS platforms with minor exceptions in PID namespace. The reason for those exceptions is that inconsistency in PID is limited. Also, additional details are provided in Table 3 and 4 of the paper. So to address soundness challenge, the key design is to establish a mapping between the host view and container view on the virtualized system resources. This mapping correlates the virtualized data with host data, and it helps provenance tracking system to use the consistent provenance data. According to the analysis in previous slide, the principal namespaces that impact provenance are PID, mount, network, and IPC. So another challenge in container provenance tracking is the clarity challenge. Without understanding the essential container semantics, we can neither accelerate the automatic analysis process nor simplify security analysis. In this paper, we provide two essential container semantic patterns and expect more patterns in the future. So one pattern is container boundary. It helps isolate the subgraphs of different containers, and we implemented by some provenance data model adjustment in Spade. The other pattern is container initialization. It marks the subgraph representing the container initialization. The implementation involves some graph analysis here. And this will wrap up the problem statement and the system design. In the evaluation, we evaluate CLARION's thoroughly in effectiveness, generality, and efficiency. The question for effectiveness evaluation is how effective is CLARION in dealing with real-world container microservice attacks? And the answer is to do real-world exploit here. We picked 3 recent vulnerabilities and brief them in this table. They come from different core components of Docker container engine with high severity. The first 2 vulnerabilities are even more detrimental because they achieve privilege escalation on container hosts. We will focus on CVE 2019-5736 run C to show the effectiveness. The exploit consists of 2 stars of the compromised container. The first star will get everything ready, and second star does the actual damage. We provide a comparison between CLARION and Spade here. Similar to what we see in the motivation example, CLARION successfully addresses the fragmentation in every invoked fork system call and eliminate ambiguities on bash executable file. Besides, we can have a clear insight about container in the graph generated by CLARION. And the same thing happened on the second star also. With the namespace and container awareness, the provenance tracking system is well functioning. The question for generality is whether CLARION solution is generally applicable across different container engines. We answer this by generating container initialization graphs and graph quantitative results for different containers. Due to the time limit, we only show the container initialization graph here. As you can see, we provide the graphs for Docker engine and Rocky engine, where boundaries of container are clear and container initialization subgraphs are circled. Important flags of clone on shared system call are recorded and namespace changes are clearly observed. The last part of the evaluation is about efficiency. We use a microservice benchmark called Google Boutique as the workload during the evaluation. The results show that the overhead added by CLARION is less than 5% in both runtime overhead and storage overhead, which we believe is acceptable. In conclusion, we find that existing provenance tracking solutions are inadequate for microservice scenarios because of being namespace unaware or container unaware. CLARION is the first namespace aware and container aware provenance tracking solution. We performed the comprehensive evaluation shows effectiveness, efficiency, and generality of CLARION. For effectiveness, we generate a sound and clear provenance graphs of our 3 real-world CVEs, which outperform the graphs generated by the traditional solutions. For generality, we show that our solution is independent of container engines by providing a container initialization graph and quantitative results for 3 container engines. For efficiency, we use the microservice benchmark to test the runtime and storage overhead of CLARION and find that the overhead is less than 5% over speed. If you have any question and feedback, please feel free to contact me. Thank you.